Okay. So the topic today is field effect transistors, in particular FET biasing. We have already talked about junction field effect transistors last Monday. Well, not this Monday, I mean Monday before that. And today we are going to try to talk about how to use the field effect transistors in amplifier circuits. And of course, in all amplifier circuits, you have to first bias the device. Basically, if you remember, we had these characteristic curves. If you plotted ID was strongly dependent on VGS. So if you plot ID versus VGS, you essentially get a graph which looks like this, a parabola. And there's a voltage at which it pinches off. So this is VP, a negative voltage. I'm talking of an N-channel JFET, the kind that we have described. And this voltage is called VP. It's a negative voltage at which there is no current. So if you put a big enough reverse bias on the gate source, between the gate and the source, the depletion region there, if you remember, this is what the JFET looks like. You have a channel which is N-type, and you have basically put a P-type region around that, and this is what the gate is. So if you put a big enough reverse bias between the gate and the channel, what is going to happen is that the depletion region is going to become so big that it's going to pinch off the channel even without any current flowing through it. And if that happens, the channel becomes non-conducting because there is no path from the drain to the source. This end is called the drain. This is the gate, and this is the source. And we have found that there is something called the Shockley relation, which relates ID to VGS. So this basically says, this is basically the value that ID takes when it sort of saturates, when VDS is large enough. So this is the ID versus VGS graph. On the other hand, if you were to plot ID versus VDS, you would essentially get a graph which looks like this. Initially, when the drain to source voltage is small, the channel essentially behaves like an ohmic resistance, so the current rises with the voltage. But once the drain to source voltage becomes large, that actually produces a reverse bias between the gate and the channel, and that widens the depletion region, lowering the conductivity of the channel, and as a result, it doesn't keep on, the current doesn't keep on rising linearly. It bends and then flattens out. And it's this flattened out value, which is called IDSS. This is for VGS equal to 0. IDSS simply means drain to source voltage with the gate shorted. And then if you put in negative VGS, which is what you are supposed to do, you're supposed to always use the junction field effect transistor in a reverse bias mode. The gate to channel has to be reverse biased. So you either put VGS equal to 0, that also produces a reverse bias because of the drain to source voltage difference. But you can actually also put in extra reverse bias with VGS, and that's exactly what that formula is telling you. If you put in extra reverse bias, the ID at which it saturates, this is really that ID that we are talking about here, this ID, that keeps on going down. Now, you might be worried about the fact that VP is negative. So this minus sign should cancel out, but yeah, let me remind you that VGS is also negative. So VGS by VP ratio is actually positive, and you're going to get smaller and smaller values the larger the magnitude of VGS becomes, until VGS reaches VP, at which point it vanishes. And since the JFET is never supposed to be used, beyond this, if you keep on increasing VGS to further negative values, the channel stays pinched off and you do not get any current whatsoever. So it's really not a parabola, it's half of a parabola up to the vertex. It doesn't go up on that side. So this is what a parabola should have looked like, but this is only half of that parabola up to this point. Up to VGS equal to 0, it's not even half of the parabola. Half of the parabola would be infinitely long. you're only supposed to go up to VGS equal to 0 because you're never supposed to forward bias the gate channel relationship, the gate channel junction. So you are never supposed to put a positive VGS. Okay. So is this much okay with everybody? And by the way, even if I don't ask a question, you'd better keep on responding from time to time. When I'm in the full screen mode, I don't know whether I'm connected at all or not. I'm just hoping that I'm still connected. So this much everybody remembers, right?
Yes, sir.
Hopefully. Okay, and there's only one more thing that I should really say, which is what I said before is once VDS has increased to a large enough value, ID saturates and it becomes completely flat. Now that's not exactly true. It doesn't become completely flat, but it becomes almost flat. It rises very slowly with VDS. So that is going to come in handy when we talk of the AC model, to remember that this is really not completely flat. But for most practical purposes, it's almost completely flat. Remember, this equation tells you that once you have reached saturation, this equation only works for this region, or rather for this region, once saturation has been obtained. And remember that this equation, of course, doesn't have any VDS in it. That means, according to this, the Shockley relation, ID should not depend on VDS at all, provided you have gone into saturation, of course, provided you're beyond this region. In this region, ID, of course, strongly depends on VDS. There it behaves like an ohmic conductor with a slightly variable resistance. On this side, it behaves essentially as if ID is fixed, but it just does rise very slowly. Okay. Now, as you all know, if these are the characteristic curves, when you want to actually use this as an amplifier, you would want to bias it at some region in between, so that when you fluctuate around that region, you will be able to get, it will not not actually drive this all the way up to the drain voltage or cut off and so on. Now, there's also another reason why you have to be careful about biasing when you're dealing with FETs. The characteristic curves of FETs are a lot more nonlinear than for BJTs. Note that there's a parabolic relationship here, right? So these curves are not really, if you were to plot them for equal intervals of VGS, these curves would not really be equally spaced. There would be either big gaps or small gaps around. So on the higher end, there will be big gaps. On the smaller end, the gaps will be much smaller. That's a property of the parabola, right? Because if you look at when you are increasing the VGS from here by this amount, the current only rises this much. Because the same amount of increase here, increase meaning actually decrease in size, actually increases the current a lot more. So the characteristics being inherently nonlinear, you have to be careful to choose the region where you want to bias it, because your behavior of the circuit will depend strongly on the biasing. Okay. So having said that, let's now take a look at the simplest biasing circuit, which I've already drawn for you. I've already drawn it for the simple reason that my drawing skills are very limited, and especially if I try to draw a resistance, somehow I always end up drawing something which looks horrid. So I took some time and carefully drew out the resistances here. And this essentially is the simplest amplifier circuit that you can make with a FET, junction, JFET. And let me just get rid of all this extra stuff from here, so that with the characteristic curve, we are going to need it, but we'll draw it again then. So this particular circuit has two resistances only, two batteries. There's a VDD, that's of course a battery. There is other VGG. VDD is of course connected between this point and the ground. VGG have shown explicitly where you're connecting it. There are two capacitors, and whose job essentially is the same as the capacitors you saw in the BJT circuit. Basically, the job is to ensure that the DC part of VI does not flow in and change your bias, or whatever biasing you have done here is not affected by whatever source you connect here or whatever load you connect here. The capacitor essentially disconnects this part of the circuit from the source or the load as far as DC is concerned. And of course, we assume that the capacitors are large enough in size so that once the frequency reaches reasonable values, where regions where you want to use the circuit as an amplifier, the capacitors basically behave like shorts, so they can be ignored. So these capacitors basically are there to protect the biasing and make it independent of the source and the load voltages, or source and the load resistance. It's more important. Okay. So other than that, this is a very simple circuit. You have just two resistances, two batteries, and one JFET. That's it. And by the way, we know that there's an N-channel JFET from the symbol, because remember this arrow that we put on this gate. This arrow essentially shows that this is like the diode arrow. This is like, it says this side is P, this side is N. So it says gate is P, the channel is N. Okay, so now the name of this kind of biasing circuit is fixed bias. And analyzing this circuit is absolutely trivial. All you do is you find out that you need to find VGS to be able to use this formula. VGS is, of course, the gate voltage minus the source voltage. Okay, by the way, whenever we denote a voltage with a single letter, that might look like a problem because a voltage is always a voltage difference. It's never really a voltage. At a point, you always talk about voltage difference. So when you say voltage at the gate or voltage at the source, what you always mean is voltage of the gate and the source, respectively, with respect to the ground. So there is some point which you designate as the ground. Here the circuit clearly shows that this point is the ground. And when you say VG, you mean the voltage of the gate with respect to this point. And when you say VS, you mean the voltage of the source with respect to this point. VG will be again the voltage of the drain with respect to this point, the ground. Now, VGS is of course the voltage difference between the gate and the source. It's the voltage of the gate with respect to the ground minus voltage of the source with respect to the ground. Now, question, how much is VS? Tell me, in this circuit. How much is VS and how much is VG? These are the two questions. First, how much is VS? The easy question. The voltage, the DC voltage at the source, how much is that?
0.
Have to be 0, right? It's directly connected to the ground. That's a simple thing. What about the gate voltage? Now, what the gate voltage, you have to remember one thing. In the gate, between the gate and the ground, you have two things. You have a resistance, RG, which is actually typically a rather large resistance, and a biasing battery, VGG. Right? However, the resistance, how much current flows through the resistance? Remember, we are talking about DC here, so this part and this part of the circuit is simply not here. You can simply forget about that. So how can you figure out the amount of current which flows through this RG? Any current here, where will it come from or where will it go? Even if you don't remember anything about FETs, this has nothing to do with FETs really. This is more about basic circuit analysis. This current here, where can it go? This of course can flow like this, right? But then it has to complete a circuit. Can it go through this? That is, can current flow between the gate and the channel? Of course, here you're talking about between the gate and the source, but if you remember the way the thing looks, this is the gate, this is the channel, and this is where the source is. This is where the drain is. So current has to flow from the gate to the channel and then into the source. But can it do that? At least can substantial current flow? By the way, gate is P-type, channel is N-type for us. And so this, remember this is almost like a diode, this part. And that is exactly what this arrow is supposed to remind you of. There's a diode between PN diode, where the P side is the gate and N type is inside is the channel. So how much current will flow in this situation?
No current.
Minority carrier will flow through the gate.
Minority carrier currents can only flow, which is very low. So no current is not exactly right, but almost no current. Okay. So that is one of the reasons why the JFET has where the GFET has an advantage over the BJT. But the JFET draws very, very little current from the input side. Through the gate, almost no current flows because the gate is always bound to be reverse biased when it's operating. And through a reverse biased PN junction, very, very little current flows. So how much will the drop across RG be? Ohm's law. If very little current flows, remember whatever current flows here, that has to go through RG, right? This is the loop. As far as DC is concerned, the source is out of the circuit. So is the load, but right now we are interested in the source. Source is not in the circuit. So any current has to flow like this. Now, gate to source, the current is almost zero. So the current through RG will be
Nearly zero.
nearly zero. The voltage drop across RG will be
Nearly zero.
good. So how much will the voltage at G be? VG, how much is that? You have to just start from G and go to the ground and see what voltages you encounter on the way. The drop across RG is nearly zero. Then what do you have? When you are going from gate to the ground, what else do you have?
GG should be minus GG.
It has to be minus VGG, right? Because that's a drop. We are looking at a drop, looking for a drop between gate to ground. But when you go like this, you're going from the negative end to the positive end of the battery. So you get minus VGG, which is, of course, perfect. You want the gate to be reverse biased, right? Gate has to be negative with respect to the source. So VGS is simply minus VGG. This is the simplest calculation. There's only the battery, nothing else. So now that you know VGS is minus VGG, can you find out ID? IDSS and VP are parameters for the JFETs. Supposedly they have been given to you. Yes? Anybody? But how do you find out ID?
From the Shockley relation.
Just from the Shockley relation. You just take the Shockley relation, you know IDSS at least. If you know what the parameters of the JFET are, you know IDSS, you know VP, you just plug them in. And you now know VGS. So you just plug it in, minus VGG. By the way, this is less than IDSS because VP, remember, is negative. So although I'm writing 1 plus VGG by VP whole square, this is not more than 1. This is actually less than 1. So ID takes some value, which you can calculate directly. Okay. So fixed bias calculations are trivial. You can directly calculate them. Okay. The only other thing that you need is the voltage at the drain, VD. So how much is VD going to be? Yes?
VDD minus IDRD.
Yeah. You start from the battery here, you know the voltage here is VDD. Then you go down, this current is ID. I should have actually indicated that already because I am talking of ID a lot. So VDD is the voltage here, IDRD is a drop across RD. The voltage at this end has to be VDD minus IDRD. And that's it. Okay, by the way, these are, strictly speaking, I should really say this is VGSQ, IDQ, and this is VDQ, or which is the same thing, VDSQ. Remember, the source is connected directly to the ground, so VD and VDS are the same thing. And I hope everybody remembers what this Q is. Q stands for quiescent. That is, how much currents and voltages you have in the circuit when there is no signal. And when you apply a signal, the signal makes the voltages and currents fluctuate about this quiescent point. The quiescent point calculation here is rather trivial. You just calculate, you use VGG to calculate VGS, and then plug that in, you get ID. And then you just use Kirchhoff's law, or actually Ohm's law. You're just saying IDRD is a drop between the VDD and the drain. That's it. And you're done. You have found out all the quiescent point voltages and currents. Just one question. Why do you have an RG at all then in the circuit? Let's see how many of you can figure that out. Notice that RG carries almost no current as far as biasing is concerned. So RG, drop across RG is 0. So suppose I just shorted RG out. If the drop across RG is 0, putting the RG or not putting the RG makes no difference. So why don't they just short it out? Why do you need an RG at all? Okay, hint. You have to remember that this circuit is an amplifier. That is the hint. When I say you have to remember that this is an amplifier, what I mean is it's not enough that this actually just you get its bias right. For the bias, as you can see, RG is not needed at all, right? Nowhere in this equation did RG make an appearance. Yeah. In this whole thing, no RG anywhere, right? So, any reason why you would want to use RG? Apart from biasing, why do you need, what do you have in an amplifier? What else do you need to do? Or what else are you worried about when you're talking about an amplifier?
So feedback.
Stability of bias.
Stability of bias, and then somebody says?
So
Those
feedback.
are issues about how good the biasing is. I'm saying apart from the biasing. That's about how good the biasing is. Right? Feedback improves the biasing. True. But I'm not worried about biasing right now. I'm saying that if you have an amplifier, what is the job of an amplifier, by the way? Is biasing the job of an amplifier? Biasing is something you do because you have to do it to make the amplifier work. But do you build an amplifier to bias it? Why do you build an amplifier?
For the gain.
Yeah, that means for the gain of what?
Input
For you
signal.
to have a, yeah, you have to give a signal and the signal gets amplified, right? That's the job of the amplifier. Biasing is just incidental. The amplifier will not work without the biasing. That's true. So you have to, of course, be careful about the biasing. You have to ensure it's stable and all that. But the question that I was asking is, why do you use the amplifier? You use it to amplify things, right? So frankly, you have to apply a signal. And the signal, of course, goes to VI. And since that's an AC, and if you assume that the frequency is high enough, You can essentially think of the capacitor as a short. But now can anybody tell me why you need the RG? I've already told you why you need the RG, but you should be able to explicitly tell me. Without the RG, what will happen? When you're considering considering AC, you're supposed to actually just worry about the AC part, right? It's the superposition principle which you're using here. For DC, you calculate using the DC part. For AC, you calculate only using AC part. So in AC, what is VGG replaced by when you do AC analysis? VGG is a fixed battery, right? When you're doing
A short.
yeah, you replace VGG by a 0 volts or a short, right? Now, can you now see why you need an RG? Without the RG, what would have happened? VGG is a short. For AC, VGG, this part is a short. Okay? This part just is like a shorted wire as far as AC is concerned. If RG had been 0, then
VI will just connect to ground.
yeah, so basically VI will be shorted to ground. Two problems there. One is VI, what will happen basically is if VI is connected to the ground, then is the gate really which is directly connected to the ground. So how much will the signal be? So remember, the gate is where the input voltage goes, and that controls the output, right? That's your Shockley relation. It says that whatever the gate to source voltage is, that controls the ID. Now, if you were to have a short here, how much would the gate voltage be? The AC voltage at the gate. How much of the signal will be across the gate? You say that right now. So if the RG had been 0, what would the AC signal be at the gate? Gate is just this point. How much would the signal be there?
It would be 0 signal.
It would be 0, right? So how can it be 0 when you are connecting a source? Basically, the source has its own resistance. So the entire voltage will drop across the source resistance. Of course, for that to happen, it might be that the current would have to be huge, and that huge current might even damage your source. But even if your source were not damaged by the large current, the upshot would be you would get no signal. If the gate has no voltage signal, no AC voltage signal, that means the gate voltage will not fluctuate. It will stay at its DC quiescent value. And if the gate voltage doesn't fluctuate, neither does the current. So everything will be fixed. But here, everything being fixed is disastrous, because that would mean that you will not get any amplification whatsoever. So RG is necessary not for the biasing, but because of the presence of the RG, and in fact you take quite a huge value of RG, somewhere of the order of mega ohms, so that basically very little current flows ultimately, so that no drop or very little drop occurs because of the source resistance. Almost the entire source voltage goes to the gate, and that is what helps in amplification. Clear? Now, you have to be careful about how big RG is. You use RG of around a mega ohm. You don't use RG of, say, a giga ohm. Why? Because the gate to source voltage is gate to source current. The minority carrier current is of the order of a nanoampere. You don't, even with a mega ohm resistance, can safely ignore IGRG for DC, because IGRG is around millivolt then. But if you use a giga ohm resistance, 10 to the 9 ohms, then of course you will not really be able to ignore IGRG. Okay. But if you put in a mega ohm resistance, which is typical, that will give a huge input impedance. Remember, there are two ways for which the source current can flow. Once it comes in here, it can go here or here. Very little current flows here. And if this resistance is large, very little current will flow here too. So the source will deliver very little current. And that's a good thing, because then the source resistance will not affect the output at all. Okay, so this is basically the idea behind the fixed bias circuit. Very simple in calculation, but you have to be careful and realize that every part of this circuit has its purposes. Okay, now everybody take down these numbers. You can see on the screen IDSS, VP, VDD, RD, RG, VGG given. So these are just parameters given, which you should be able to use to just solve this problem. So you wanted a problem, this is the problem. This is a problem which you don't have to submit, but the job is to find out the quiescent point values for this set of numerical parameters, for this value of IDSS, for this value of VP, and so on. So please take these numbers down. I hope everybody can read them, despite my rather bad handwriting. Is that done? So just take this circuit, use these parameters, find out the quiescent point voltages and currents. Okay, but let me just, so as you can see, you can calculate the whole thing with just the Shockley relation. You don't really have to go any further. That's all you really need. But the graphical analysis of this particular problem actually becomes rather useful in understanding certain features. So let me just remind you of what the graphical analysis would look like. So for that, all you need is the ID versus VGS graph, which is what I drew at the beginning. This parabola, which cuts off at VP. This is IDSS. So that's the parabola which gives you ID versus VGS from the Shockley relation. We need one more, of course, ID and VGS. These are our two unknowns here. So we will need one more equation, but we already have that equation, which is we know VGS. VGS is minus VGG. So if I were to plot this relationship, VGS is minus VGG on this graph, what will that graph look like? What will the curve for that look like? Can anybody tell me that? I want to plot this. VGS is minus VGG on this graph. What will that graph look like? That curve look like? I already have one curve. Of course, if I get another curve from this, where the curves intersect, that will give me the quiescent point values. Anybody? What does this graph look like? This equation look like when you graph this on ID versus VGS graph. This is class 10 actually, not even class 11 or 12. So if you had an XY graph paper where you had to plot x equal to minus 5, which is essentially what this is like. What does that graph look like? What does x equal to minus 5 look like on the XY graph?
Parallel to y-axis.
Yeah, it looks like a vertical straight line, right? VGS is some negative constant. That's just a vertical straight line. This size is VGG. That's it. Right? It just looks like a vertical straight line. That's the other graph. And where they intersect, this point gives you your quiescent point value. This is the IDQ. Of course, you already know what is VGSQ because that's already known. It's fixed at minus VGG. But anyway, the x and y coordinates here will give you the VGS value at quiescent point. It will give you the ID value at the quiescent point. You're done. Right? Okay. Clear? So that's the graphical construction. Although, frankly, this is so simple that you shouldn't really have to worry about a graphical construction. But the graphical construction is actually important because it demonstrates one thing. Suppose I were to replace my JFET. Suppose it has just burnt out and I had to replace it by another JFET. Now the other JFET would typically not have exactly the same characteristic curve. Even if it came from the same family, IDSS and VP are rather fickle parameters. They keep on changing from JFET to JFET. So maybe your other second JFET has a characteristic curve which looks like this. So notice your ID changes this much. Quite a lot, actually. Okay. So this is really not that great for, as far as bias stability is concerned. If you change your device, which you may have to because your device, or even if your device just grows old and changes, its parameters drift with time, you will have quite a large shift in the quiescent point value, and such a large shift that it might really make the whole problem undoable or make the circuit unworkable. Okay. So this is the same kind of issue that we saw with the BJT. In a BJT circuit, the easiest possible biasing circuit, the fixed bias circuit, is very, very simple, but doesn't really work very well because if there's a drift in temperature, drift in the parameters of the transistor because of aging, or because you have to change your transistor and hence beta changed, your bias point would change a lot. The same problem comes in here. With JFETs, thermal stability is not a huge issue, but aging, of course, is, and the fact that you may have to change your JFET and replace it with something else with slightly different parameters is also quite a concern. So the fixed bias circuit is easy to understand, easy to analyze, but not that great as far as applications are concerned. So what do? Well, you do something which you also saw with the BJT. This is called a self-bias circuit. In the BJT circuit, you saw that you would put a resistance in the emitter bar here. Here you do something very similar. You put the resistance in between the source and the ground. And did you notice anything else? Something else is missing here in this circuit. Something that was in the fixed bias circuit. What has gone missing?
VGG.
Yeah, VGG. You don't have a VGG any longer. Now, why did you need the VGG? The VGG was essentially there to reverse bias the gate to source or gate to channel, basically. The reverse bias the gate channel junction. Right? That's why you needed a VGG. Here, there is no VGG. Why is that a good thing, by the way, not having a VGG?
It cut out the cost.
Exactly. As I have said several times, if you use 2 batteries, you nearly double the cost. Once again, the JFETs and the resistances are almost zero cost compared to the batteries. So using 2 batteries would double the cost. This has roughly half the cost because you don't need 2 batteries. However, the real question is, how do you reverse bias without the battery? And the answer is simple. How much is VG here? Okay, this is the gate. How much is VG? Okay, let's use blue pen to write this. Just so that yeah. Again, I'm talking about the DC part. How much will VG be? The voltage difference between this point and this point. Come on. The voltage difference between 2 points which are separated by resistance. Class 8, I guess. Or 7, I don't even remember when we first learned Ohm's law.
Current into RG.
What into RG?
The current into RG.
The current into RG, but how much should the current be? The current in this, where will it go? There's a capacitor blocking DC on this side. Okay. You can't have a current just hanging around. It has to go somewhere, right? It can't go this way. Where will it go? Can it go this way? Yes? Remember, when you are operating a JFET, the gate to channel is always reverse biased. So how much current will flow? Yes?
No current.
How much current flows through a reverse bias? Gate to channel is like a reverse bias diode.
So the saturation, like there's a small amount of current.
Not saturation. Saturation is a matter between drain to source. Remember, the drain to source is basically like a piece of semiconductor, right? You just have a channel. Ideally, it should just have, if you just had the channel, nothing else, didn't have the p-type doped into it, it would just behave like a conductor. Okay. The reason why the channel becomes narrow, etc., is because you have a p-type semiconductor built in, which produces a depletion region and all that. But here we have a gate to channel. Gate is p-type, channel is n-type, and is reverse biased. How much current would flow? You've already said this before. Just the minority carrier current, nothing else. That means a very tiny current. That's the rule, right? That is why the JFET is such a great circuit as far as input impedance is concerned. It draws almost no current because it's essentially the reverse biased PN junction. So VG is how much? For all practical purposes, it's 0. Okay, it's a nanoampere times RG, which is of the order of mega ohm. So it's a millivolt order thing. But it's really 0 for this set, for all practical purposes. How much is VS? This is the source, this is the drain, right? How much is VS? VS, remember, once again, is the voltage between the source and the ground. And how much is that? So how much is the current flowing through RS? Can anybody tell me that? At least one of the currents that has been indicated in the circuit, ID. Okay, that's given. Okay, that's not given. You have to find it out. But in terms of ID, can you tell me how much current will flow through RS? ID is the current flowing into the drain. That's it. How much flows through the gate? Again, there are 3 ends, right? Drain, source, and gate. ID flows into the drain. How much flows through the gate? I'm repeating myself, but this is important.
Through the gate 0.
Through the gate 0. So how much flows through the source?
So ID only then.
Exactly, ID will have to flow out, right? That's Kirchhoff's current law. Current in equals current out. There is no way current can go through this, which actually makes analyzing FET circuits way easier than BJT circuits, because in BJT, you have all 3 currents. Of course, there you have to say that the base current and the collector current, it's a collector current, emitter current has to be base current plus collector current. Right? That's a Kirchhoff's current law there. Here, Kirchhoff's current law would simply be ID goes in, what goes out has to be ID. So now can anybody tell me what is the voltage at the source?
IDRS.
Exactly. So how much is VGS?
Minus IDRS.
Exactly. VG minus VS minus IDRS. You needed a reverse bias. You needed a negative voltage between the gate and the source. And you've got it. You have, without a battery, you don't have a battery here, but you still have a negative voltage because the current flowing through the source, that produces a voltage drop between the source and the ground. Since the gate is at the same voltage as the ground, there's a voltage drop between the source and the ground. The ground is at a lower voltage, and so gate is at a lower voltage. Okay, right? So the gate is now at a lower voltage compared to the source, which is exactly what you need. But now notice that here VGS depends on ID. So now if you go back to your equation, the Shockley equation, IDSS into 1 minus VGS by VP whole square, you get IDSS into 1 plus IDRS by VP whole square. So earlier, for the fixed bias circuit, what you had was an explicit formula for ID. Just you knew VGS is minus VGG, just plug that in, you get ID. Here, what has happened? Can you find out ID from here? Can you find out? Remember IDSS, RS, IDSS and VP are parameters for the JFET, which we know. And RS, RG, RD, these are things we know. We are connecting them, so we know how much they are. Can I find out ID from this? Of course, when I say ID, this actually is the ID quiescent. Just the biasing, no signal. Can you find out ID from here? Yes or no? I'm not asking you to find out the value. Okay, typically, people tend to avoid questions like if when you're at a party and somebody comes up and asks, do you remember me? It's best not to answer if you don't, because the next question would then be, if you say yes, the next question would then be, tell me who am I? So I'm not doing that. I'm not asking you to solve for ID. I'm just asking, can you find out ID from this?
Yes.
Yeah, how do you find out ID from this? Again, I don't want a solution, but how do you proceed? What kind of an equation is this?
By solving the quadratic.
Yeah, this is a quadratic equation. You solve it, you find ID. But quadratic will give you two roots, right? Which one would you take? Okay, for that it's best to just look at, yeah?
The non-negative one.
Non-negative in sense, non-negative what? Non-negative value of ID. Actually, this you can show pretty easily from the algebra, or pretty easily just from the graph that I'm going to do, is that both the roots are going to be positive for ID. In fact, if I drew it, it would be obvious. Look, this is your ID versus VGS graph, where the curve is like this. Of course, the equation that I've written down, the quadratic equation, would have given you a parabola, but you really have half of a parabola. And so this is the Shockley relation, this red curve, and VGS is minus IDRS. What kind of a graph would that be on this? We are plotting an ID versus VGS graph, and you have this relationship. What kind of graph would you get?
It's a
Straight line with a negative slope.
Straight line with a negative slope going to the origin, right? Right?
Yes, sir.
Yes, sir.
So this is, okay, let me now try my hand at drawing this. Okay, let me use this a bit. This is the draw line feature. Yeah. So this is the equation that you get from the self-biasing part. This is just Ohm's law, or you could say Kirchhoff's law. And this is the Shockley relation. Now notice, where would the other intersection be? There's only one intersection that you can see here, which is this one. And so there's only one value for IDQ. This is the ID quiescent. And this value gives you the VGS at the quiescent point. And unfortunately, here, the other root would not be negative. The other root would also be positive. Some would be somewhere here. This parabola, where the parabola goes and cuts the straight line. Okay. That's at a positive ID. But that would give you a VGS which is less than VP, or less than minus VP, and you don't want that, right? Because your equation, ID equal to IDSS into 1 minus VGS by VP whole square, is valid only up to minus Vp. Beyond that, ID is 0. Beyond that, the ID just flattens out. This channel, once you have pinched it, if you increase VGS even further, it's going to stay pinched. No current will flow. Okay. So the way to find out the right root is simply the smaller of the two roots. That's it. You don't need to go more than that. Just a smaller root will do. Both roots are positive for ID and both roots are negative for VGS. It's just that one of them gives you a VGS value which is smaller than the pinch of voltage, and that, of course, is unphysical. Okay, clear? Yes?
Yes, sir.
And now let's compare what would happen if you were to change the JFET so that you have a slightly different curve. Say, this orange curve is for another JFET which you have replaced your original JFET by. Notice that the quiescent point values are things that you want to maintain. So I'm going to compare between the fixed bias circuit that we had a while ago and this one. For the fixed bias circuit, to get this VGS at quiescent point and this ID, what you would need is basically a VGG which is equal to this in size, or minus VGG, this being equal to minus VGG, and this is what the fixed bias circuit would give you. Okay, my drawing is a bit bad, so let me just try drawing this curve a bit better. Let's try, although there's no guarantee that it will be better this time, but still. Okay, not much better, but still. So for a fixed bias, this VGG curve, VGS curve will be straight meaning vertically up. This is also a straight line, but going like this. Okay. So can you see what advantage you have now with this circuit? Despite the quadratic equation that you have to solve, so slightly worse as far as calculation is concerned.
The change of the quiescent point is much smaller than the previous case.
Right, because you have a flat, the vertical line here meant that this was the change in the ID. Now you see the change in ID is a lot less. Okay, and it's the ID change which you worry a lot more about, because any change in ID will also change the VD, and that will have a bigger effect as far as the behavior is concerned. So here we have managed to reduce the ID change simply by replacing a vertical VGG line by a slanted VGG line. So question, suppose I'm not satisfied with this. I want even less change in ID. Can I do that?
Then we should increase the value of RS.
Yeah, but if you just increase the value of RS, then the straight line will be something else, right? The straight line will be this. And that would mean your quiescent point would shift. I want to keep the same quiescent point. You're very right. Increasing the value of RS would mean that you get a flatter curve. So this becomes even flatter, so this change becomes even less. That much would be right. But increasing the value of RS would change your quiescent point, right? So if you wanted the same quiescent point, yet wanted this line to be flatter, can you think of a way of doing that? You cannot do it with this equation. Why? Because in this equation, you know that the graph has to, because you are insisting that the graph goes through this point, quiescent point is fixed, and you know the graph goes to the origin, right? When VGS is 0, ID has to be 0 in this equation. So it has to go through the origin. So 2 points on the straight line, given the straight line is fixed, right? You can't change the RS now. But increasing the RS is the right way to go. But if you were to increase the RS here, make this curve flatter, or make the straight line flatter like this, then this straight line would no longer go through the origin. It would go through some other point. Can you see how you can achieve that? What would the equation of a straight line like this be? VGS equal to minus IDRS will not work. You need something else. you need to ensure that when ID is 0, VGS has a positive value. So how do you manage that?
Plus some constant.
Plus a voltage, right? So if you could add a bias battery here, but not reverse biasing, but actually forward biasing, but not enough forward bias to overcome the IDRS. So you still get reverse bias, but basically you make this curve flatter. That would, of course, reduce your increase in ID, shift in ID because of various changes in your device a lot smaller. So this is even better. What's bad about
But
this?
sir,
Yeah, go ahead.
so you're not changing the slope, right? You're just adding a constant that will just shift the line.
No,
I guess.
no. I'm also changing the slope. I'm increasing the RS because I want to go to the same point.
Oh, okay.
Okay, so if I start here, go to this point, that's one slope. If I start here, go to the same point, because I want the same quiescent point, right? Because I want the intersection point not to change. So I have to increase RS. This RS is not the same as this RS. This RS is actually larger. Has to be, because otherwise, if you start here, you would have gone like this. You would have ended up with the quiescent point here. You have increased the RS so that you get the same quiescent point. Okay.
So we are adjusting the values of RS and VGG to get the same quiescent point.
Right, but you are increasing you're adding a positive VGG to allow you to get the same quiescent point with a bigger RS, right? In the self-bias circuit, the one which we reviewed, the moment you have a fixed some quiescent point, then RS is automatically fixed because it has to go through this line, right? You know this equation goes to the origin. You know this equation goes to this point. The line becomes fixed. That means the slope becomes fixed. You know what the RS has to be. Here you want to increase RS beyond that. So in order to achieve that, you have to use a positive VGG. What's bad about that? What's bad about using a positive VGG? That is, the only thing that you would have to really do is just put a battery here. VGG. That would get that. That would give you minus I. That would tell you, if you put a battery here, remember once again, there is no drop across RG. So that would just replace VG by VGG plus VGG. So this will become plus VGG, VGS. Exactly what we want, a flatter straight line. What's bad about this?
Sir, in case of FET, all time gate and source should be.
Yeah, but as long as you do it carefully, the IDRS will overpower this VGG. I will choose VGG small enough. I will not choose a huge VGG. Where calculated right, that shouldn't be a problem. You're right that if you are using a positive VGG, there's a chance that it might end up forward biasing the gate channel. But that we will not do. We will be careful. Apart from that, what's bad about using this? Come on. You told me that at the very beginning. What's bad about using two batteries?
Cost.
Yeah, but how do you make the circuit believe that there are two batteries even if there are not?
A potential divider.
Exactly. So the final circuit that we have is this. That's a JFET circuit. Very nice circuit. Uses more resistances than before. And I've shown you that the RS is actually in practice shorted out for AC because you don't want feedback provided by the RS. This flattening out of the curve is good for stability of your bias, but it's bad for your signal. So you essentially put a CS across it just for the same reason that you put a CE across the RE in the BJT circuit, BJT is common emitter amplifier circuit. And here, exactly for the same reason, you use a potential divider bias, which makes this look like, again, use Thevenin's theorem. This will look like a voltage source in series with a resistance. It will look exactly like this. And you will have the advantage that you don't have to use a second battery, but your circuit will have effectively a second battery. So the circuit which is commonly used is this one. Very similar to a CE amplifier circuit, but the biasing part almost the same. The AC part, the amplification part, quite different. We are going to discuss that on Monday. So let me just stop here. I've just run out of time also. Okay. Oh, I'm running.
So,
Yeah.
So I didn't understand one thing. Like you said, like when applying AC signal to VGG, it'll act like a short.
Which one?
Uh,
Because
huh?
remember, when you do AC analysis, your job is to just look at the AC part. So every voltage source, if you have a DC source, it has to be replaced by its internal impedance. And the internal impedance of a DC source is, if an ideal battery is zero, of course, it would not be a short in reality. It would be a resistance of a few ohms, whatever internal resistance the battery has. But if you have just a few ohms on the path, that will still not limit the current. The current will become huge, and the drop across the source's own resistance will become so huge that you will get almost nothing. Okay?
Oh, okay, sir.
So you're doing superposition. Remember, when you're talking of DCs, you just take the DC. When you're talking of ACs, you're just using the AC. One more thing, why can you use superposition despite having nonlinear circuits? That is because you're just using small signal AC analysis. You're going to replace the AC by its linearized version. The circuit element by linearized version for small signal. Only because of small signal does superposition work. For large signal, superposition doesn't work. But the basic idea stays the same. A DC source has no AC in it. So it behaves like a zero voltage. Okay.
Oh, okay, sir. And just one more small thing, can I ask?
Yeah, you can ask, except that unless you have a class after this.
No, sir. So in the assignment, like whenever like you're not assignment, like whenever you reference like a small signal AC circuit, does that mean like a VCC is zero?
No.
Like you did in the lecture, like you took VCC
No,
to be zero.
VCC 0 means exactly the same thing. When you're analyzing the AC part, look, you're not saying that there is no DC. You are saying there is a DC and there's a fluctuation around the DC, and you're just worried about the fluctuation now. Okay. VCC equal to 0 will make the circuit collapse. It will not work. The circuit has to have the right amount of DC around which it can fluctuate. When I say, when you are replacing the VCC by a short for a small signal analysis, you're just analyzing the AC part. So once again, exactly the same reason as this one. Why do you replace VGG by 0? Because you're not interested in the DC part any longer. You're just interested in how much AC does this contribute. VCC is the power supply. It is supposed to be fixed in time. So it contributes pure DC. At least that's what we hope, or that's what we believe it should. Okay. Of course, it might be possible that your power supply actually fluctuates in time, and that produces an extra signal effectively. That actually messes up your circuit's behavior. You have just ignored that for the time being. So assume that your power supply is good enough.
So if there's a like non-zero VCC, I can just like ignore it and continue.
There is a non-zero VCC. It's not a question of if there is. There has to be a non-zero VCC. But the non-zero VCC for AC part, for the AC analysis, you have to replace every DC supply by its internal impedance. And here we have just assumed that the sources are good sources. They have very little input impedance, so they can be replaced by shorts. That's for the AC analysis part. It doesn't mean that VCC is really zero. Because if VCC had been zero, then the bias would have gone wrong. And if the bias goes wrong, your circuit doesn't work. Okay?
Okay. Yes, sir. I was getting a little confused, like how it was
The AC analysis is done separately because of that. It's just like when you do superposition with multiple sources, you take one source, find out its result. You take the other source, find out its result. But when you're taking one source, you replace the other source by its internal impedance. Here, the DC sources, you take them to get the biasing. For the AC part, you just consider the AC signal. And the DC parts, you replace by the internal impedance. And the actual answer is the sum of the two. But because you're interested only in the fluctuation around the bias point, You don't worry about this adding up, this addition that you should do at the end for the superposition principle. You don't bother doing that simply because you're interested in the variation anyway. Right? So you could add the DC back and say, okay, this is the voltage, but you're not interested in the DC part. You're interested in the signal there. So you don't bother adding back the DC part. That's all there is to it. Did I make sense?
Oh, okay, sir. Yes, I got it. Thank you.
Okay. Bye.